Before I start with the slides, I would like to show some of these pictures here, because they all will have a huge relevance in the future. First of all, this all of you should know. This is just one of the most valuable resources in this century, because we talk on lithium. Lithium is like the gold or the silver of the centuries in the past. And I'm for sure Saudi Arabia have been never that rich in oil than what lithium means for the region here. If this lithium is converted, then we talk on battery plants. This is just a picture from a battery plant. The renewable electricity, which on we finally talk, can be harvested with wind farms, solar photovoltaic on rooftops, or large power plants. Both is possible. And this is something very special. We see since a few years nowadays more and more startups in automotive industry, which did not happen the last 40 years. So Tesla is I guess, the most known example. This is a small startup in Munich in Germany, and it's difficult to see for you, but on the surface of the car there are solar cells integrated in the car. And that means for the solar irradiation in the summer in Germany, if the car is outside, it has the chance that at the end of the day, the car can drive 30 kilometers longer, because the solar cells charge the car. So it has even not to be recharged if the distance is not that huge. And this is something very, very new. I will come later on to that back, because surprisingly, during this century, carbon dioxide, CO2, will become from a huge waste, which is still today and will be in the future, a raw material. Because we still need hydrocarbons, which is gas, petrol, or chemicals for chemical industry, and they're all based on hydrocarbons. However, they can be also produced with very, very low cost electricity, water, and air. And from air, we need the CO2. So that will be very valuable, but I come back to that. And of course, this is the resource, but this we will see very soon. I may take the chance in the very beginning to tell you what should be the key takeaways after more than an hour, and then you can check when on the way I would like to go into more details there. So first of all, we have a massive pressure due to climate change that we terminate the current energy system and establish the new one. And that has to happen very fast if we would like to survive on this planet as a human species. Finally, it will be a fully renewable energy system, and this is nowadays rather well understood that it can be technically done, and economically it is very attractive. What is needed to understand how such a system works, that we can model it before it's built. So we can do some, a view into the future, how it may work, and that has to be done for all hours of a year. And the reason is the sun is not always available, the wind is not always available, when we need grid interconnection, when we need storage, and due to that we have to do it in a very high temporal resolution. The key components for the future are solar photovoltaics, wind energy, batteries, and then technologies, they're summarized as power to X, because that means we start with electricity and we end with something else. That can be a fuel, that can be a chemical, it can be clean water for water desalination, and this is all summarized with power to X. What is more and more clear nowadays, that solar photovoltaics will be the dominating source of energy in this century. Not only electricity, it will be energy. The overall energy system, the major dominating source will be solar energy, also here. With this transition to a fully renewable energy system, we can really stop these greenhouse gas emissions, which drives climate change. And we can even reduce the cost, and we can create a lot of jobs. So from a policy perspective, a perfect match. Electricity demand will drastically rise due to the broad electrification of the energy system. So that means all energy we need for heating, for transport, for seawater desalination where it's needed, For running the industry, in the very end, almost all of that will be based on electricity. And the reason is electricity is so, or will be so low cost, and it's very efficient to use electricity. Latin America, and I think there everyone here can be very proud on, owns the best resources in the world, not only really in the world, for solar, for wind, for hydro, and for lithium. So it's a kind of a paradise place from that perspective. No one else in the world has better resources. However, what is also part of the fact, other world regions also have good resources, but they may be 10% less good. So there is still need for hard work. Energy-intensive products have the least cost globally in Latin America in the 21st century. So that means all products which are based on a lot of energy demand, they will be in the very end based on electricity, and it's not surprising. In the places in the world where electricity has the lowest cost, these products will have the lowest cost. So this is an outstanding competitive edge. And I think what is absolutely not understood at all, that we will be very soon, maybe end of this decade, early next decade, in particular here in the region, so Altiplano, or when we talk on the overall Atacama Desert, we will talk on around $10 per megawatt hour what electricity really costs there. And no one has yet understood what this means, because never in history we had so extremely low cost levels of electricity, never with hydropower. This is half of hydropower, even a third of hydropower. This is a complete new order. And that has the consequence that energy-intensive products have a huge advantage to be produced based on this low-cost source. So enormous economic rise is possible. However, that we learned from all regions in the world, good governance is needed to allow the harvesting of the benefits. And substantially more studies are needed to better understand this comparative competitiveness, because this is a complete new energy world. I would like to explain a bit more. Okay, the first bullet point was climate change. This is a report which had been published by IPCC, which is the United Nations panel of the climate change researchers. It was published last Monday, the so-called 1.5 degree Celsius report, because this is one of the main, if not the main, targets of the Paris Agreement to fight against climate change. And it might be a bit difficult for you to see, but this is the current level of greenhouse gas emissions, which is 40 gigatons of CO2 in the world. And in the year 2050, so which is only 30 years ahead, a bit more, these greenhouse gas emissions have to be practically zero. And this is an enormous pressure. So that means all investments today in coal will be for sure lost, because they need 40 years, 50 years to run their investments, but in 30 years' time it has to be zero. So investments in coal are gone. Just last week I had a meeting with large, long-term investors in Sweden, and they already told me they do not have any more investments in coal. But what they start now is to sell, or to check their portfolios, that they sell investments in oil and gas, because this is the next what has to be stopped. Gas, by the way, is the last one, so maybe also good for Bolivia. So for the next 15, 20 years it should be safe, but in 2050 there will be no natural gas anymore. And it's simply not allowed. And then even worse, and maybe this is the main message of the report, from the 2050s onwards to the rest of the century, we need to have net negative emissions. And this is outstanding challenging. So that means every year we need to extract more CO2 from the atmosphere than what we emit there. So that is really, really challenging. And let's see how we can organize that. And what will be the options to get CO2 out of the atmosphere? One of the easiest and most natural ways what we could think on is to have growing forests. But currently we are a stupid species on this planet, because we crop down forests. We do it the other way around, and everywhere in the world. It's not only in Brazil, where of course it also happens, but it's also in Indonesia, in Malaysia, in Africa, and it's outstanding stupid. So we have to stop as soon as possible to crop down forests, and to reverse it, we have to grow forests. But that will be not enough anymore. Because the problem is these negative emissions will be 10 to 20 gigatons of negative emissions per year, and currently we emit 40 gigatons. So all what the world population emits, and with the huge emitters, the United States of America and China and Europe and others, all what is emitted today in all energy sectors, half of that has to be removed from the atmosphere from now on in 30 years. This is outstanding challenging. So the consequences we should stop as soon as possible. And the impact of climate change comes very soon. This is just a satellite picture from last week. It's Hurricane Michael, which destroyed major parts of Florida. And we know it from last year, where several islands in the Caribbean have been destroyed, fully destroyed. So there have been islands where 95% of all buildings have been fully destroyed. And this is currently the global temperature rise is 1.1 degree. This is a nice warming up what will come. So we do not really want to live in a 1.5 degree world, and for sure not in a 2 degree world, and for sure not more. And maybe our society may not survive it. Okay, so the problem is really huge. The question is where these emissions come from. So most is CO2, roughly 80%, and then methane emissions, and then some other greenhouse gases. 2/3 of these emissions come from the energy system. It's transport. Just look on our cars, planes, all these vehicles emit greenhouse gases. Electricity and heat sector, and then industry sector. Industry, there, for example, cement manufacturing is 5% of global greenhouse gas emissions, steel industry is 5%, chemical industry is 5%. All those industries have go to zero globally. Land use change I've already mentioned. Most of that is still cropping down forests. And then agriculture, this is something we all have to be very worried, because most of this agriculture is simply breathing cows. Because cows or cattle, they breathe out methane, which is a very strong climate greenhouse gas. Or if we have rice plantation in water has also methane emissions. And that we will not get to zero, no chance at all. But since we have for the total system to achieve zero emissions and later on even negative, it's absolutely clear that in the energy system there is no greenhouse gas emission allowed anymore. So that means by 2050 fossil fuels will have to go to zero. And that will require very strong, ambitious and actions, and finally policy measures. Now is the question, if we understood what in principle we should have to do in the next decades, is the question, what are the principal resources on a global scale we have available? On some specific places, there is always the one or the other resource a bit better, but this is a global perspective. So first of all, this is roughly the energy demand represented by this bubble, what we really need. It will grow, but this is roughly what we need. And then is the question what we have available. So this is wind. And you see, already with wind, we could run all the energy demand in the world with wind alone. But it would be not a low-cost energy system. But in principle, it would be possible. Here you see biomass. This is already limited. So in some places in the world, we have more biomass available. In others, we have less. But all in all, it will not work, or not as a sole solution. Hydropower had been developed for the last 100, 120 years. And it's a very attractive source of electricity, but we do not have enough water and rivers in the world to run our energy demand based on hydropower. Geothermal energy, we just heard it in the speech before, this is available in the world. However, it's also limited, and the best places in the world for that we have to live on a volcano, and not so many people in the world live on a volcano, luckily maybe. And then of course we have the sun. And here you see, with this huge amount of energy from the sun, we could run by 1,000 times all our energy demand in the world. So sun alone would be more than we will ever need. All our future generations will ever need. Sun delivers much, much more. But of course, the optimal solution is a mix of all of them, because this will provide a lowest cost energy system. Now let's go a bit through what are the main technologies, what are their main features. So this is Solar photovoltaics, you saw the picture in the beginning, it can be put on a house if the roof of the house allows it, so it depends on the roofs. It can be built as a power plant. This is a photovoltaic power plant. They're built nowadays up to many hundreds of megawatts. I think the largest which is currently built is in India with 2,000 megawatts. And so they can be built from a small system with a few photovoltaic modules, panels, up to sizes which are larger than the power supply of entire countries. And everything in between is possible. So it's a very modular technology. And what is also very attractive, it can be used for off-grid electrification. So this is the house of a very poor family in Ethiopia in Africa. And here is a small photovoltaic module. And this is the first access to electricity that they can get there. And the first electrification for such very, very poor regions is typically light in the evening hours, charging the mobile phone, and maybe listening to a radio. So this is the first electrification typically, but with off-grid systems, one can go up to power an entire house with TV and refrigerator, with a freezer. This is all possible. So everything in between can be designed. It's just a question of whether people can afford it. Here you see a solar map in the world, and you will see several more of them later on. And let's focus here on Bolivia. And this is the best solar site in the world. So there is no place in the world where the sun is more intense than here. Maybe a bit south of here, but roughly here in the region. Others are also good, as we know. Southwest of US, Mexico, the entire Sahara Desert, Southern Africa, Western Australia, Middle East, Central Asia. But from all of them, the best is here. So, and this means this 10% better than all the others. But all the others is 25 or 30% of the world. So from that point of view, this energy is available everywhere. And what is even more important, so I live here, so it's more in the north, and the sun is not that perfect, in particular not in the winter. But the point is, from the best sites in the world to such, let's call it moderate sites, there is roughly a factor of 2. So if here the costs are very, very low, then in almost all places in the world it costs not more than a factor of 2 more. So the consequences is everywhere in the world a very low cost source of energy. And maybe one point to mention more is what are currently the efficiencies of these modules. Maybe I should mention for these modules first, this is the only electricity generation technology without moving parts. So it's only a passive element, we put it into the sun, and from the 2 cables we get electricity. This is outstanding cool from my point of view. Because all other technologies, something has to move. And this makes it more complex, higher in operation and maintenance, or shorter lifetimes, and so on. So this is an outstanding advantage. And by the way, for understanding the physics, how this can work, Albert Einstein got the Nobel Prize. And I think it was really worth that. But the point is, it's so complicated, it took 100 years that the technology could be really used on a broader scale. The current situation is that the most modules one can buy in the market are 18–20% efficient. So that means from all energy from the sunlight, 18 to 20% is converted into electricity. However, and this is most attractive, the theoretical limit is around 80%. So that means in the decades to come, what we will observe is year by year, these modules will be higher efficient. But the good message is there is no need to wait, because it's already today in most parts in the world the least cost source of electricity. I'm for sure for more than 50% in the world, there is no lower cost source of electricity than solar photovoltaics. Even this year by famous Fraunhofer in Germany, it was published that in Germany, solar photovoltaics is the lowest cost source of electricity for a new built power plant. And Germany is here, so it's not this red, perfect here. And wind is also good in Germany, but solar is lower in cost. And that gives you an impression what it means for all those Sunbelt countries all around here. So it's already today highly attractive, very low cost, but this will continue. And that's a really strong message. Wind energy. Wind energy, first of all, is also available all over the world. So that means the higher red you see, again, as before, it's a really good site. But it's not anymore that perfectly distributed as solar. Here you see solar. It's really well, evenly distributed all around the world. This is not anymore the case for wind. And of course, this is also an observation in Bolivia. There are some sites where wind is really good, and in other places it's not so good. And you can see it here. So there is a region at the border to Paraguay, so Santa Cruz, and then southeast, where it's a really, really good place for wind energy. But you can compare it to other places, in particular in the rainforest region, their wind energy is not that perfect. But all over the world, we always find very good wind sites in all major regions. And again, the best wind site in the world is here in Patagonia, which from my point of view is even fair, because two countries share this wealth. So it's Argentina and Chile, both have access there. And this is the best wind site we can find on ground. So it's even very challenging to build the wind turbines there, because almost the entire year the wind is blowing there. So it's not so easy to get it installed. But as you can see here, so there is good wind resources, and in particular in the Northern Hemisphere, so Canada, US, Europe, Russia, wind will be very important, because solar energy is not so perfectly available in the winter half year, but wind is very good in the winter half year. And then the least cost solution for the energy system is to use a lot of wind in the winter half year and a lot of sun in the summer half year, and then both together complement each other very well. This is also the case for Latin America, but not on the scale as in the Northern Hemisphere. But as you can see here in the southern part, wind is excellent. Here, Bolivia to Paraguay, it's excellent. In the northeast of Brazil, it's excellent. We know some places in Mexico where it's really good. So we have several good places where the wind resource is really good. And here in a bit more detail, I zoomed it out that you can better see it. So this is Bolivia and Paraguay. I've zoomed out here. And you can see in the entire southern part of Bolivia, there is outstanding, excellent solar irradiation, but the same is for nearby Peru, Chile, Argentina, so they all have access to excellent solar resources. So from the energy point of view, this is the fortune of Bolivia, I would say, because this is the least cost site in the world to produce electricity in this century. Other sites are not better, maybe except here. They're very similar, but this region is the best in the world. And this fortune waits for harvesting and utilization. Here is wind. And here you can see at the border to Paraguay, so Santa Cruz and in the east or southeast, where the wind potential is really good. So in other parts, in particular what I mentioned before, whenever there is rainforest, wind is not really of much help. But here in that region is really good, and that could help to run the energy system on a very low cost level when solar and wind is used. And here is a description. I have to explain a bit that you can better understand it, how valuable that is. So here you see it again for the region. This is the real weather year 2005, so a few years in the past, but almost all years will be comparable. Here you see all days of a year, so 365 days. And here you see the 24 hours of a day. And what you see then around noon, there is almost continued perfect sunshine. And the reason is that it's so close to the equator, so there is no much change of the position of the sun during the year. And due to that, the solar irradiation is almost perfect. So the place where I live, there is almost no sun in this period of the year and in that period of the year. And most sun is here. So this is one of the best places because it's so stable. And that means if there is a solar system, whether it's on rooftop of buildings or power plants, if that is combined with a battery, then electricity is used during the daytime. The battery is charged during the daytime. From the late afternoon onwards, the battery is discharged due to the next morning. Then is again sunrise, and then it starts again. Direct use of electricity for all what we run here with electricity. The batteries are charged again over the daytime. Starting from the afternoon, solar irradiation goes down, the batteries discharge, which provide us the electricity to the next morning, and then it starts again. Day by day by day. Extremely stable. That's perfect. The wind resource is available over the year, but more in the months of the middle of the year. So not so much by the end or beginning of the year, more in the middle for the region. But all in all, it's good distributed. There are other regions in the world where it's more compressed for a specific part of the year. But here you can see here is more wind, which is, by the way, not so bad, because this is the part of the year where the sun is slightly lower. So at least here you can see good wind starts where sun is a bit lower. But all in all, it's perfect, and with solar alone, everything could be run in principle. Okay, now let's come to batteries. So batteries have two main applications. They can be stationary. So this is in a building in Europe, and this is the battery, by the way. You may even not see it. So it's nowadays even a kind of a lifestyle element. So people could have a kind of a nice picture or art or what else on the wall, or such a battery. So that's a bit strange from my point of view, but anyway, so if it helps to get batteries into the market, it's good. Others just put it into the garage, so both is possible. But this is a stationary battery for a house, and this is the most successful product launch we ever observed in history. This is the Tesla Model 3. Within the first 4 to 5, 6 weeks, they sold products in the value of $12 billion and more. This never happened before in history, and since that time also not. So currently they have, as Elon Musk called it, the manufacturing hell. So they have now to deliver these 500,000 cars to all the customers, and they have to produce them first. And they have all the background in IT, and now they have realized that real hardware manufacturing is really different than only writing a computer program. But anyway, they manage it. So in the last months, they had a steep increase in manufacturing of the cars, and they sell it. And this is really, I would call it a killer application, because it's the first electric car with a long range on a really affordable price level. It's not any more extremely luxurious car as a Model S or something like that, but it's really a mass market, and that will change it, or change the situation, and you can see it here. So these are statistics, how electric vehicles are sold in the world, and the annual growth rate of the sold cars is 70 to 80% year by year. This is outstanding growth. So, and it continues now for several years. This is driven by China, so half of all electric vehicles in the world are sold in China, because I think China was the first country in the world which really understood what is the potential and dimension of this technology from an industrial perspective, but also from an environmental perspective. Of course, most of the 20 most toxic cities in the world, they're all in Asia. 19 of them are in India and China. So most toxic cities in the world are in China, and they have to get rid of air pollution. And one option is to get rid of coal-fired power plants, and the other option is to get rid of all combustion cars. And for the combustion cars, they do it, but of course they also need, the rest of the planet also need cars. So currently we have 1 to 1.2 billion cars in the world. Mid of the century, we will have something between 2 to 3 billion cars. And my guess is 90–95% of them will be battery electric cars. And just have in mind, they all need lithium. So that's a really cool market. Okay. And what is the good thing? So the cost of lithium batteries go down. So this is from financial community, from Bloomberg. And the cost decline currently is 10–15% per year. And it's not so relevant what is the lithium price, because from all materials needed for a lithium battery, there is a very small fraction of lithium. So there is some price flexibility possible, I would say. But what brings the cost down is really establish huge manufacturing plants with automatized manufacturing, with very large economies of scale that reduce currently the cost. And as said, it's a decline of 10 to 15% per year. And then just imagine what this means in 5 to 10 years. So it costs a fraction of today. And then these batteries are everywhere. So that's really great. And now this power to X as the last major component, I wanted to explain you roughly. So we start with electricity from solar and wind. Then there is a so-called electrolysis unit. Electrolyzers, they have as an input electricity from here. It can be every kind of electricity, so it was invented more than 100 years ago. So it's old technology from that point of view. But of course, to have a sustainable green solution, it needs to be renewable electricity. And this is done from solar and wind. But it could be also from hydropower or geothermal, by the way. But the largest sources in the future will be solar and wind. So, and then this electrolyzer, they use electricity and then water. And the water is split into hydrogen and oxygen. And most of the energy is then in the hydrogen. And this hydrogen is then combined finally with a carbon atom. And the product is a hydrocarbon. And this we call diesel, petrol, jet fuel, all these hydrocarbons, or chemicals. So the chemical industry in the world is based on fossil oil, fossil gas, and coal. But this all can be substituted with that process. And finally, the CO2, if we do not have a better CO2 source, then we can extract it from atmosphere, surprisingly. And it seems to be affordable. So in the very end, we can produce these hydrocarbons with very low-cost electricity, and that needs to be really very low cost, and then water and air. And at my university, we had just in the last year, there as a demonstrator, and it's really no rocket science. It had been 3 standard shipping containers. In one shipping container, there was this electrolyzer unit, so to convert water with electricity to hydrogen. In a second container, there was a CO2 direct air capture unit, so to extract CO2 from the atmosphere. And in the third shipping container, there was a unit to convert the CO2 and the hydrogen to fuels. And that was just to showcase it can be done. And even this last conversion step there, this was also invented 100 years ago. At that time based on coal, but as said, it's not a big challenge to base it on electricity. So this is all available technology. That really makes it valuable. This is just a kind of indicative diagram for the chemical industry. So we finally start with CO2 and hydrogen. Here it's already syngas, which is carbon monoxide, but in principle we can start with CO2. And with this Fischer-Tropsch process, we can convert it to diesel, to petrol, even to the products. Based on that, we can produce plastics or other things, so that's very valuable. We can convert it to methanol. Methanol is one of the basic chemicals which we use for production of plastics and other chemicals. Or we can produce fertilizers. There we also need the air, but not CO2. We take the nitrogen from the air, and then with hydrogen, and then we get ammonia, and this is the starting point for all fertilizers we use in nowadays agriculture or agricultural systems. So from that point of view, we always need air and low-cost electricity and water. That's it. For the final step, before I show you more results, I would like to tell you what is really the value of efficiency. So we will have huge efficiency gains in the energy system which is currently built up. And I would like to show you the main examples from electricity, heat, and transport. So electricity, what we have today, if we have thermal power plants, most electricity today in the world still comes from coal-fired power plants. And honestly, this is like 5,000 years ago, sitting in caves. We sit around the campfire, and this is burned with coal. This is what we do. But nowadays, we live in the world, almost all, or every one of you, we have all these smartphones. We live in the world of electrons. We are not anymore in the cave and sitting around the campfire. But our energy system is still that. So if we have a coal-fired power plant or nuclear is nothing better, then most of the fuel which is used to run this plant is finally losses. It's thermal loss. We cannot use it. It's extremely inefficient. So in the very end, the overall efficiency of all thermal power plants in the world as an average is only 35%, and the other 65% is fully lost. So the minor share is electricity. And now compare that to solar and wind. Solar and wind, we harvest the renewables, and almost everything is then converted to electricity. This is a complete different level of efficiency. And just have in mind what for huge effort we have to do for this fuel. So this coal has to be dug out somewhere in the ground, it has to be processed, it has to be transported. The same we have to do with uranium, we have to transport it around the planet. This is a huge effort. For that 2/3 in the end is thrown away due to technical and physical reasons. Well, that's highly inefficient. Heat, there it's better. If we burn something and if we have perfect furnaces or ovens, then we have efficiency 90% up to 100%. That sounds really good, and it's not bad, by the way. However, we can do it with electric heat pumps, where we take a lot of heat from the environment, driven by an electric system. There we can have efficiency of 300 to 400%. So in other words, we put 1 unit of electricity in, and we get 3 to 4 units of heat back. And again, you see this factor of 3. So from using only 1/3 or converting to electricity, here we get 3 times or even more heat out. This is really a huge jump in efficiency. And the same is with cars. Honestly, the cars we use today is a shame for engineers. And the reason is that the average efficiency of such a car is 20–25%. So we put fuel into the tank, whether it's gas or petrol, doesn't matter, or diesel, it's all the same. And then we have roughly 25% of this energy is converted to power at the wheels. If we now compare that to an all-electric car, there we have an efficiency of 70–80%. And the reason is, again, we don't burn stuff. So we are not anymore in the cave. We live in the electron age. That's the difference. And again, it's a factor of 3. And this will be huge efficiency gains in the energy system which is currently built up. And by the way, this is the reason why we see these renewables and this broad electrification everywhere. With this efficiency gain of a factor of 3, it's not surprising that these solutions cost less. And if they're economically more competitive, then they run through the markets and they squeeze out these old inefficient solutions. So this is also a very key driver. Last year had been in Hamburg, it's located here, a G20 meeting, so that means the leaders of the 20 economically most powerful countries meet from here and there. And a large international NGO asked us to show what is the competitiveness without subsidies or other effects in the year 2015, so more or less now, and what is the competitiveness of the renewables compared to the conventional solutions, which is nuclear, coal, and gas, in the year 2030. And whenever something is indicated in green, here for one of those 20 countries, then it means renewables are already lower in cost than oil, gas, coal, nuclear, if it's built as a new plant. If it's orange, then it's very close, and if it's red, then it's not yet competitive. So that had been the state of the development in the year 2015. And now let's see what happens in 2030. And we have not done the calculation because we have been not asked for that, but I'm for sure the same is in 2025. So the consequences, every country in the world which want to achieve or maintain international economic competitiveness has to switch to renewables, or they will lose the economic competitiveness, because it's simply the least cost source of energy, which is the driver for the economic development. And this had been understood very early in Germany. The current government is not anymore that extremely clever in that. Hopefully they catch up again. But it had been also mainly understood in China. So China has the largest program in the world to develop renewables. And a few years ago, they have been followed by India, which is, I think in 4 years' time, the country in the world with the largest population. By 2050, they will have around 1.7 billion people. China then 1.3. So for a survival strategy on our planet, it's absolutely clear India and China have to go in the right direction. Otherwise, we others in the world can do whatever we want to do. It will not change anything. But luckily they have understood. So the clear strategy in India is to have an energy system fully based on solar, because this is their resource number one. And in China it's a mix of solar and wind. And of course we know there is huge capacity of coal-fired power plants in China right now, but there are energy scenarios within China, and they clearly indicate by 2050 they should have 90% renewables, by a much higher level, of course, of electricity demand in 2050 as today. But the clear message is all leading countries in the world will have to go for renewables, or there will not be any more leading countries. That's very clear. When it comes to the G20 members in Latin America, so it's Mexico, Brazil, Argentina, they have outstanding, excellent renewable resources, and their renewable energy policies, I would say they go in the right direction, but they could be much more ambitious. But this much more ambitious, I think, is true for almost every country in the world. And then is the question, what is a kind of a limit? So if the renewables are so attractive, can we run a world on 100% renewables? Is that possible? And that's quite interesting. So at the last climate conference, the International Climate Conference in Marrakesh, no, it's not the last, 2 years ago, there are around 50 countries have decided to target 100% renewables. Many of them are island countries, so if we do not switch very soon to renewables, they will be simply flooded. Of course, they are in the Pacific. So they're not on 2,000, 3,000, 4,000 meters as here. So they are maybe on 2 or 5 or 10 meters. And if the average of your country is, let's say, on 7 meters, the seawater level is rising by 1 meter, and you get a really strong storm with a flood, then everything is flooded. So it's really strange for them. However, we see also more and more growing number of different countries from Latin America. For example, Costa Rica may have the most aggressive target here in the region, but also Denmark and Sweden. There it's more wind. And I think what is most important for all have been 3 weeks ago in California, where the governor of California approved a law that in 2045 all electricity supply in California will be practically renewable. This had been done before on Hawaii, also in 2045, for 100% renewable, but California on its own is the fifth most powerful economy in the world. And that's, of course, completely different order. And luckily, what we know, if something is successful in California, 10, 15 years later, the rest of the US is doing the same. So that's a very good signal from that point of view. And we have nowadays not only hundreds, more than 1,000 cities in the world with a 100% renewable energy target. And this is most important because finally the practical change is done on a level where really the real people decide. So it's not on a federal level, maybe even not on a state level, but really where the people do the decision making on investments, and this on a city or municipal level. So that's really great, and it's all around the world. And we have also a growing number of companies with 100% renewable targets. So it's a kind of a push for the society from everywhere. That's really good. Before I show you some of the results of our modeling, I want to briefly explain how we do that. So, sorry for this more technical slide. So it's more data preparation. Then we have a strong position that people should be allowed to fulfill their energy demands on their own first. So that means when everyone of us here in the room as a private person has the idea to do self-supply with own, typically photovoltaic on their own house and their own rooftop, in almost all countries in the world this is not forbidden. So people are allowed to do that, of course with different levels of freedom and legislation. But in principle it's allowed. And due to that we build it as a strong part of our model that if people decide on their own first to invest in their self-supply, this is taken into account first. And we see that very strongly. For example, the best example maybe for that is Australia. For the last several years they have built close to 1,000 megawatts a year of PV, and this had been mainly done by citizens on their own rooftops, or retailers as companies or larger companies on their industrial rooftops. but it's mainly to only supply their own demand. So that's really strong, but we see the same in California or in Europe. So due to that, we did it first, and then we have the standard sectors of power as of today, then heat and transport, and different industrial sectors. They're not yet all industrial sectors there, so we would like to use next year a bit more to have their steel, cement, and chemical industry in more detail. And then we will have the overall energy system there. And then we get huge amounts of results, and that we have to structure and visualize. Here you see some icons, what we have there. So we have 5 different types of solar. This is fixed tilted PV, then one axis tracking following to the sun, which would be the most preferred option here for this excellent solar conditions. And then we have 3 types of rooftop systems. They're technically very close, but from the business case, they are different. So this is for residential houses, for commercial buildings, let's say retailers or smaller companies, and then larger industrial customers, because they are large industrial rooftops where one can put several megawatts of PV on a single roof, and they're really large roofs, and of course they have a different cost. Then wind onshore and offshore in water, hydro in run-of rivers or in hydro reservoirs with dams, and geothermal energy of course is there. Concentrating solar thermal was a lot of discussion in the last, I don't know how many decades, but currently they're not competitive to solar photovoltaics. And what is currently built in 2 weeks of solar photovoltaics have been historically built in concentrating solar thermal. So from that point of view, the technology is close to be out of the market. And then bioenergy in different forms. We use only waste and residues for sustainability reasons. We don't use energy crops in our model. And then we have different types of storage. So pumped hydro storage, which is the most used storage for electricity today. Then batteries, but also compressed air is possible, or power to gas, where we can store electricity to be converted into gas, methane, and that can be seasonally converted in gas turbines back to electricity if needed. Then different demand sectors for energy transition, of course. There are also coal and nuclear power plants. Of course, we have gas turbines, and larger regions are interconnected by grids. So this is the power system. And for the transport system, which was currently introduced in our model in more detail, we have the road segment, so everything what drives on the road, cars, trucks, buses, two-wheelers, delivery cars, then rail, then marine, so ships, and aviation. And the fuels we can use for that is electricity. We call it liquid hydrocarbons. That can be fossil fuel, biofuel, or synthetic fuel. Methane, which is finally gas, natural gas, can be fossil gas, biogas, or again synthetic gas, or it can be liquefied. So nowadays, natural gas is traded around the planet in form of LNG, liquefied natural gas. And then direct hydrogen, but hydrogen has been always to be gained by one of the other options. And all these different fuels can be typically used for all those options here. Maybe I do not go to more detail here. Now let me show you our results on a global scale, and of course I will always point a bit out what it means for Latin America. So the world we have structured in 145 regions, and I have to think, I think including with Mexico it would be around 20 for Latin America, so Argentina are 3, Brazil are 4, and so on. And all in all we have 9 major regions in the world. And it's the first, it's the first model in that, or the simulation in that detail for energy transition which had been calculated for all hours of a year. So we really know that this energy system is finally stable because all hours of a year are covered. And this is a really, really important result, which was also surprising for us as modelers, and it took us half a year to check again and again and again all what we did there, but the result did not change. So let me explain. In the year 2015, the electricity generation in the world had the highest share with 40% of coal, 25% of natural gas, 16% of hydropower, 4% wind, 1% solar, a bit oil, and 10% nuclear. So this is how the average in the world works. And our result as a least cost, so other options would cost more, as a least cost result in 2050 is fully dominated by solar. So more than 2/3 or around 70% of all electricity from solar photovoltaics, around 20% from wind, 10% from hydro, and then all the rest. And here you can see how this evolutionary changes. So this is the system as of now. And you see hydropower does not change much because most of the large rivers in the world are already fully utilized by hydropower plants. So there is not so much additional potential available. And then you see a strong increase in wind energy and in solar photovoltaics from now to 2030. And this is all over the world. However, then something happens which is quite interesting from 2030 onwards, mainly solar grows. And this has finally three main reasons. Reason number one is the cost of solar photovoltaics continue to decline because it's the least complex electricity generation technology of all, and we know since many decades how the costs continuously decline. And currently there is nothing what tells us that this cost decline will stop in the near future. So continued decline of cost, and please have in mind it's already today the lowest cost source of electricity, but that will continue. Number two is that to overcome the day-night issue for solar, we need low-cost batteries. And again, year by year, the cost of batteries will go down, and that in addition will push more usage of solar. So this is the second driver. And then the third driver is what you cannot see directly, but most of the additional demand of electricity in the world from 2030 onwards will be from Sunbelt countries or from the Sunbelt regions where 2/3 of world population is living. So it's entire Africa, entire South Asia, of course Latin America, and this all in all maybe around 5 billion people. And there the main additional electricity demand in the world will happen from 2030 onwards. And since almost all of those countries are in the Sun Belt, most of the additional energy will, due to that, come from solar energy. That's rather obvious then. And here you can see how it really works in an evolutionary way. And then, of course, the question is, if it's so dominated by solar, can it be really true that solar can be so low cost? So this is just a recent publication from a European technology and innovation platform for PV. So many European experts on solar photovoltaics are there together and have done this report. So I'm one of the steering committee members of this group, and it's for the advice of the European Commission. And here you can see the different main solar photovoltaic segments. So residential, these are smaller scale systems on the rooftops. Commercial, up to 50 kilowatts, that might be smaller companies, larger retailers on a shopping mall, something like that. Industrial, so for larger industrial companies, and then utility scale, and there are 50 megawatt is a kind of a building block. So if you would like to build a 500 megawatt PV power plant, then you would build maybe roughly 10 of these 50 megawatt plants next to each other. So it's all modular. And what will be the cost right now? The cost right now for a solar photovoltaic power plant in the world might be 500, 600 euros per kilowatt. And maybe in the most competitive markets in the world, such as in India, you would get it for less, I assume. So due to some policy changes this year in China, the cost of photovoltaic modules in the last half year dropped by a next 25%. So this, you have to be paranoid to work in this industry due to that situation, because it happens again and again and again. But of course for the customers it's great. Now it's extremely low cost. So in the international markets, these photovoltaic modules cost now as a specific price 25 to maximum $30 per watt peak. And that should be then lower than these lines already here. The report had been published last year, but this is the common fate that the cost go down faster than you can publish these reports. This is then the distribution of all 145 regions in the world with the solar share. As said, the average with 70%. And you can see in the Sun Belt it's really high. High means 80–90%. You might be a bit disappointed that here for Bolivia it's so small. It's maybe a model artifact how we have defined it, because in this large region we cannot model it in much detail with many hundreds of regions. This is even maybe computationally at the edge that it's really possible. So due to that we have in one region Bolivia and Paraguay, and then you can imagine that the huge hydropower potential of Paraguay is then allocated for the entire region. But I can assure you, if we would focus Bolivia on its own, it would be mainly based on solar as neighboring countries. So if you have a look on Peru, we know, for example, for Peru, there is excellent hydropower. And even if there is excellent hydropower, the solar share is 50%, as you can see here. So for Colombia, where hydropower is not that perfect, it goes then up to 60%, for example. And this is a clearly indication for Bolivia on its own, it will be 60–70%, I'm sure, as for other regions here as well. What it means for storage, just compare this again, 2015, 2050. So you see this kind of a storage capacity. Today, this is pumped hydro storage, and in future, this is by orders of magnitude larger. This pumped hydro storage is still there, but this is this very small green fraction here, and the rest is all batteries. So batteries will be the storage option number 1, and there is no number 2 and 3. So it will be the dominating storage, and the reason is it's the perfect support for solar due to this day-night complementarity. And it's also quite interesting, it's difficult to see, maybe 1/3 of the storage will be close to the end users. So for this residential, commercial, industrial, prosumers, prosumer is the word for producers and consumers, because finally they do both. And 2/3 will be then, at least with this setup, utility scale batteries, so larger scale batteries that balance the generation of larger power plants. I think this is something nice you could play with. We put it 2 years ago into the web. You find it here with that web address, and this presentation will be available. So I'm for sure there is somewhere then a link where you can download it. Otherwise, you find my email address there or my Twitter account there. So contact me, then I can send you everything. However, we have all these 145 regions there. So this is Latin America. And for the case, if there would be already 100% renewables for 2030, how it would work for all hours of a year. And that's really nice. You can here click on the play button, and then all hours of a year run through, and then you can see each single hour how it works. And even in the night when there is no sunshine, then you would see there would be discharge of batteries to cover the demand. And if you don't believe, you can go deeper. There is a download button, you can download that, and that you can do for all regions in the world, even with some different scenarios. And that we did to really overcome this myth that if there is no sun, if there is no wind, everything would collapse, because this is simply not true. And here we show it for all parts in the world, how this could work. And then, of course, the question is if such an energy transition is done. So from a technical point of view, we know with unlimited amounts of money, we can do everything. So currently a good example is a nuclear power plant. We can build a nuclear power plant, but it costs 4 times more than a new solar plant. So in this region, maybe even 6 times more. So from that point of view, technically it's possible, but economically it doesn't make any sense at all. And due to that is the question, how would such a transition to very high shares of renewables work? And here you can see the current cost in the world is around 70 euros per megawatt hour as an average for all what we have installed in the world and what we use. And this cost can be then roughly stabilized 60, 65 euros per megawatt hour for the next 15, 20 years. And then you see increasingly tendency to decline the cost. So they end between 50 to 55 euros a megawatt hour compared to 70 in the beginning. And the reason is very low cost solar photovoltaics plus batteries. Batteries again is this red part, and the blue part here is wind energy. So we can get to a more sustainable energy system with less environmental impact on a lower cost level. I think that's really attractive. And I would also say it's a huge business opportunity, because here you can see what huge investments are needed. So this is in capital expenditures. And here you can see that in particular in the next decade there will be huge investments in solar and wind. And also in the next decade it will drastically rise. Everything what is red is finally, let's say very colloquial, is your business case, because all this requires batteries. And if batteries are needed, then lithium is needed. And if lithium is needed, it should be really valuable for Bolivia. What does it mean for the jobs? So currently in the power sector, all that has to do with electricity, we have around 20 million jobs in the world, and half of them has to do with coal. This is the reason why all countries where we have coal workers, there is extreme strong policy against renewables, typically from labor unions. We know that in the US, so Donald Trump is just an archetype of that. But in Europe, we have it from Germany and Poland, where it's a huge problem. It's in South Africa a problem. So we have several countries in the world. Whenever coal workers are involved, renewables have a difficult standing. Nevertheless, it will change. And then in 2050, if we have an energy system in this, we call it best policy scenario, because we're not sure whether policymakers will be that clever to go for that, but we hope, because it's also the least cost solution. And you can see a lot of jobs are created. So the jobs will be roughly twice as high as today. The electricity demand would also double. So that means, in other words, the jobs per generated electricity would be more or less stable. But of course, then a lot in solar, wind, and battery. And what is not shown here, most of them are in operation and maintenance. And these are the most stable, most attractive jobs. So there are, of course, a lot of jobs in manufacturing and construction, but the jobs are dominated by operation and maintenance. And this is for the greenhouse gas emissions. So currently, a quarter of all greenhouse gas emissions in the world is from the power sector. And here you can see with such a scenario, it can steeply go down to zero, which was even surprising for me, that around 2040, which is here, we can be already very close to zero and still on the pathway of a least cost transition. So it's not that it costs us extra money, we earn extra money because we have lower cost. And I think this is a different story compared to what is typically told. We have compared that to other major energy scenarios for the global transition which are available. This can be from the International Energy Agency. Then there are oil companies, so this is Exxon, for example. Shell would be here. It can be from NGOs, Greenpeace and WWF. It can be from academics, here MIT in the US. It can be from advisory boards, here from Germany. It can be from IPCC. And then we did a kind of a comparison in just a few categories, whether these scenarios really fulfill what we need for the mid of the century. So is the energy resource base okay? So do they use resources which are really available? Have they taken climate change into account? What is about the societal cost? So societal cost might be, for example, air pollution and other facts, or wars about energy resources. Energy access for all, so has really every person in the country access to electricity, to modern forms of heating or cooking, and is all energy demand included? And then you can see there is not a single scenario which is fully on green, and this is really a disaster. Even our own scenario will be not on green because we have not yet all energy sectors there. So due to that also not, but for the power sector I would say it will be close to green. And then you can see that major stakeholders in the world fully fail, and this is a shame. So the International Energy Agency, it's a governmental organization, and sorry to say, but finally they have to do what the major governments tell them, and the major governments in that field is France, Canada, and US, and they all block renewables due to different reasons. And the consequences, the scenarios are not so helpful. So when it comes to renewables and International Energy Agency, be very careful. Take it as a very worst case assumption. In particular for solar, from my point of view on solar photovoltaics, they have not much clue. And the reason is for the last 20 years, all their projections have been wrong. And 20 years in a row wrong, and dramatically wrong. So that's not acceptable at all. And of course, it's not surprising that from all companies we cannot really expect a progressive scenario. So here you see a lot in red. Environmental NGOs are better. What is interesting from Greenpeace, there are two scenarios here. Their scenario have been done by the German Aerospace Center, which is one of the leading teams in the world on modeling future energy systems. So from that point of view, I think it's also, from the way how they did it, really okay. MIT, this is really shocking, because in principle it should be one of the best, or the best technical university in the world, so they should really know what happens. But the problem is there, you know, there is the saying, don't bite the hand that feeds you, and that's their problem, because they are flooded with money from fossil industry, oil, gas, and nuclear. And the consequences, they have to publish reports where oil and fossil oil and gas and nuclear is cherished and everything should be perfect. So their reports are worthless from my point of view. So it's a shame, they should have much better scientific standards. And one of the best scenarios is from this advisory group for the German government. It had been done 15 years ago, and they have been really forward-looking. So even today, it would be a really competitive scenario 15 years later. And they had the same solar share what we had for 2050. They had the same one for 2100, also roughly 2/3 of all energy demand. But we can now really calculate it for every hour, so that's really different. It was not yet possible 15 years ago, but it had been the same storyline. And these IPCC researchers, they're typically very conservative, so their scenarios are not so progressive, unfortunately, but hopefully they catch up. So from that point of view, you see this is still a kind of a field which requires a lot of discussion and research, and there isn't anything else than a kind of a common sense or common view. No. Maybe I do not want to go through all numbers, but when it comes to what might be installed in photovoltaic capacity in the future, so with our model we have 22,000 gigawatts in 2050, and this is only the power sector. So with demand for transportation and other sectors, it would be a factor of 2 or 3 more. And then there is this international technology roadmap of the PV industry. So they're the largest PV manufacturers in the world, have a common roadmap, and their numbers will be very soon very close, because they just contacted me a few weeks ago. They want to link their roadmap to our scenario. So that's really, really good. And maybe then we get more impact. And what I would like to show you here as an example, what is this relevance of International Energy Agency, because you will see their reports and their numbers everywhere. What is the problem there? So they have published a report in November 2016, the World Energy Outlook 2016, which is their holy book of a year, or the flagship report, the World Energy Outlook. So it was published November 2016, and they said from the next year onwards till the year 2040, so more than 20 years in the future, there should be not a single year where the annual installations should be more than 95 gigawatts. So there should be almost no growth for solar PV. Please have in mind, it's the least cost source of electricity on the planet, and our society, our civilization is hungry for energy. So there should be no much growth. And what is even more a disaster, in the year 2017, in the real world installation in PV had been 100 gigawatts. The real investments last year. So the consequences, their report from end 2016 had been for more than 20 years in the future, not a single year where in their most progressive scenario, by the way, the other scenarios are even worse, the most progressive scenario, a higher number than what had been achieved in the following year. In every normal company, you would fire this team immediately. because they have no clue what really happens outside in the world. Or they're forced, by whatever reasons, to produce numbers which are not worth the paper on what they're printed. So that's a really strong disclaimer. Be very careful when you get such numbers. Okay, now let's have a deeper look on South America. So how we have modeled South America, unfortunately with the beamer you cannot really good see it, but these are all the regions. And this is what had been by end of 2014 the installed capacity in the power sector. And this is the best quality of infrastructure investment from any of these 9 regions. All other regions in the world are worse. And what is the reason for? Half of all installation is hydropower. So a lot, of course, we know Paraguay, Brazil, but also Peru in other countries. So half is hydropower. Then you see here a bit bio, a bit wind, solar starts, then a quarter gas, a bit oil. Oil is in particular in remote areas, remote valleys, so there it's needed. And then there is almost no nuclear, and there is almost no coal. In most other regions, major regions in the world, there is a larger, much larger nuclear share and a much larger coal share. Both is a huge burden, because it's high cost, it has risks, as we saw in Fukushima or Chernobyl or other regions, or it can be very risky due to terrorism attacks. So we know there have been ongoing terrorism attacks on nuclear power plants. There was never a meltdown so far, but it's really dangerous. However, in Latin America, you can see it's from the relative development level, the best energy system in the world from the mix of sources. So that's really good. And this had been the installations in 2010 to 2014, which is a bit comparable to what had been installed. So there have been the one or other coal-fired power plant, which was not so perfect. And then, of course, gas, which is also a resource here. So all in all, it's okay. However, there should be a growing solar and wind number. But honestly, this is for end of 2014. So in the last 3 years, 3.5 years, we saw much more solar in the region, in particular in Mexico, also in Brazil, Peru, Chile. So this is growing rather fast. So that's good. This you already saw. So this is now the average for the entire region, how solar is available, how wind is available. So for the entire region, solar is really stable. So that's really excellent. It's also for neighboring regions. This is then a zoom into the resource map of solar energy and wind energy. And here you can see solar energy is available everywhere in Latin America. In the very south, it's solar not that perfect, but their wind is excellent, the best sites in the world. And when we are here in the rainforest region, then there are simply more clouds in the atmosphere, and this slightly reduces the yield of solar systems. But it's still really good. So compared to other world regions, there is nothing to complain. And wind, there it's more fragmented. So we have regions, as here, I said in the beginning, Santa Cruz, and then going to Paraguay. So there is good wind. And then entire Argentina is excellent, Patagonia, perfect, but also in the northeastern part of Brazil, it's excellent. In Mexico, we would also see good wind sites. So it's available, but not on every place. Maybe let's skip that. So this are aggregated numbers, and I show you a few of them. What would be a kind of best policy scenario development for Latin America? And this is this is Latin America, but it's not including Mexico. In our structure of the world, Mexico is part of NAFTA, and due to that to North America. So Mexico is not included here. But as you can see from the generation, as of today, it's dominated by hydropower, a lot of gas, and that's mainly the energy supply in Latin America. And for the future, hydro may grow a bit more. There will be more wind energy, but the dominating additional electricity will come from solar energy all around in the region, and maybe some sustainable bioenergy more. So there are here and there some potentials. Not surprising, so the most additional storage is then again battery, and that will grow from the mid of the next century onwards. And battery, as said in the beginning, always means lithium is needed, so that's good. I will skip here the one or the other slide to have some time for the later slides. Here you see the cost. Currently there is some really high cost due to oil-fired power plants, and that we see, I think, currently as a trend all over the world. Whenever there is a local supply mainly based on oil capacities, so diesel generators or other things, they're currently strongly upgraded by solar systems, solar alone or solar plus battery. So then the diesel plant might be still there, or the oil plant, but only for seasonal balancing or as a backup for challenging situations, and then the bulk of the electricity would be from solar and wind. And this is the key reason how to reduce the fuel cost, and then to reduce the cost, and then step by step it will be lower. Where we stopped before the break, it was mainly with the message that for the energy transition in Latin America, when we go to very high shares of renewables, even more than today, then the cost can further decline. Oops. No. Now it works. So there is the one or other diagram for Latin America on different categories. So this is the total cost of the energy system, which is for this transition in 2050 around 40 euros a megawatt hour. And this is also very remarkable because the global average is 50 to 55. So this further documents how extremely low cost the electricity generation cost in Latin America is. And this is a huge competitive edge for all energy intensive industry. So this is highly, highly attractive. So to sum this up, this transition for the power sector, first of all, Latin America can reach a full renewable energy system, and it's already today the region in the world with the highest share of renewables, by the way. No other major region in the world has a higher share today. And zero greenhouse gas emissions is well doable. It can be achieved for a cost level of 40 euros a megawatt hour, and this includes the generation, the storage, and very long distance electricity transmission, not the distribution in the regions, but the very long distance transmission. So that's highly attractive. Solar photovoltaic emerges to the most important source of electricity also in the region. So here is the number of 60%, which is only slightly lower than in the global average, and the reason is this excellent hydropower resource quality in Latin America. Batteries are most important to push to this high solar energy share, and most of the energy storage goes through a battery, and the reason is there is no much seasonal balancing which is needed due to strong seasonality. This is not so known here in the region, and due to that almost everything can be done with batteries. So the cost of storage contributes substantially to the total system, so around 30% of the total system cost is then the storage cost. As said, greenhouse gas emissions can be zero, and a fully renewable system is more efficient than all other options. And as said, we have here this report, and there are many links available. Currently, several of the links are not working, but you have just to try. You are on a website, and there you can request the document, and then someone will send you the document. But with the service provider, we have currently a problem, unfortunately. Okay, and then I would like to show you something which is maybe more an academic thing, but it's quite interesting. There have been a few years ago researchers in the US, the idea for seasonal balancing, it would be most interesting to have a direct power line connection from Latin America, or Southern America to Northern America. So the idea is, or had been, to link the deserts of Northern America to Southern America. So here you can see the generation of Mojave Desert, so in the southwest of the US, and Atacama. So where in Atacama is this here, Mojave Desert, the generation profile will be that, and then the more theoretical idea would be if both would be linked with power lines, then during the year it would be a fully stable power supply. Now is, of course, the question, and with nice publications, I think all in all 3 scientific publications. And then, of course, is the question whether this is a nice theoretical scientific result or whether this is something for the real world. And we tried then also with a kind of a simulation, but different than the US colleagues, where you see here entire Americas. So whenever there is a dot, then we have a region. And here you see that, and the strength of this circle tells you what is the energy demand and also energy generation. Here you can see the electricity demand in Northern America is much higher than in Southern America. And then we tried to remodel it with a much more or a better developed tool to really see whether this balancing here from Mojave Desert around here to Atacama Desert here would really make sense. And what we found, no, at least with our tools, it does not make sense. And you see it here in Central America that the power transmission in power lines is very, very low. So, and as a consequence, we have a large electricity system in the north, a large electricity system in the south, and not much electricity transmission in between. And the result is, or the consequence is, that this this seasonal balancing would not work. It was the first suggestion to link the northern hemisphere to the southern hemisphere, and due to that balance the seasonal variation of the sun. But we have not found that it is beneficial, and I think finally the reason is the mix of very low cost of electricity and long power lines. And the point is, if electricity generation costs 10 to 20 euros a megawatt hour, then for that distance the power line may cost 20 euros per megawatt hour transmitted or more. So the consequence is the power line is simply too expensive to balance it here. It makes more sense to balance it locally with solar and wind or hydropower and local storage than to do a seasonal balance with long distance power lines. So I guess the original authors will be not so happy about our paper. It's currently submitted, not yet published, but let's see. And here you can also see, so this is calculated for the world of 2030, if everything would be renewable. This blue is wind, this orange and yellow is solar, and the dark blue is hydropower. And there you can see in the very north of the US, it's mainly wind. In the very south of Latin America, it's also wind, and the reason is this excellent wind resource in Patagonia. This dark blue you see here in Colombia, Peru, Brazil, so hydropower is excellent in many regions here. We know also it's excellent in Canada, for example, and the rest is then everywhere solar. So from here to here, what is not hydro is typically solar. A bit wind here and there, but it's mainly solar. And this makes it so attractive that long or very, very long power lines for several thousands of kilometers, they will not pay off. Now let's come a bit more to the transport sector, because I would like to showcase a bit more what is the really value of lithium. And the most lithium demand in the future will be due to the transport sector and not so much due to stationary batteries. What you see here is a list of countries or cities, and what they all have in common that around 2030 they start to not allow any more combustion cars. So there are large metropolitan areas with several million inhabitants, and they have today announced a clear target in the year 2030. Combustion cars, as we use them all today, are not anymore allowed to enter the city. And what is allowed to enter the city is then an electric car with batteries. So that will change dramatically the structure of the automotive industry in the world, because the companies which are not able to sell electric cars, they will not sell anymore anything, in particular in those cities. But these cities are typically the largest city in their country. So there is London, there is Cape Town, so it's all over the world. It's not only in Europe, it's in all major regions in the world, or for example, Los Angeles. So it's rather clear that it will switch to battery electric cars. This is from a large Danish engineering service company. Have been recently published how they expect that battery electric vehicles will be sold in the market. So here is 100%. So these are the coming years and decades. And their key result is, for example, for Europe in 2030, around 27%, so that's here, of all new sold cars will be not anymore combustion cars. So that means that within roughly 10 to 15 years' time, the most sold cars of today are still the combustion cars. They take diesel, petrol, gas, what else? But they burn something, and within 10 to 15 years' time, this will fully switch to electric cars. And then is, of course, the question where in the world it will happen. And you see different world regions maybe 5 to 10 years later. So they did it also for Latin America, and maybe it will be 5 to 10 years later. But this is not much. So this will be a very fast transition all over the world. And around here you can see 2040, 45. They assume in all regions in the world it will be close to 100% that all new sold cars will be battery electric cars. Currently in the year it's around 100 million cars which are sold, and maybe by mid of the century we talk on 200 million. So 200 million cars in the world, and almost all or all of them will have a lithium battery, at least from today's point of view. German Aerospace Center has very similar results. And now what it means. So here you see some pictures more. The Sion I showed you in the very beginning. This is the Nissan Leaf from Japan, and it's the most sold electric car in the world. So this is more than Tesla. Most people don't know, but that's very, very successful. So in many parts in the world, the railway system is almost fully electrified. We see now more and more all-electric ferries. So that started in Scandinavia. So whenever there is a ferry connection 10, 20 kilometers, this is nowadays done based on electricity. And it costs less than with a standard diesel engine as in the past. So this is the the Tesla truck. So all electric, so there is nothing else, only batteries and the electric engine, and they use it to connect their fabs in California and Utah. And they can have a distance of several hundred kilometers, but there are more truck companies in the world doing this. So this is also done by Volvo Trucks in Sweden. They have a Chinese owner, so that's maybe very helpful to be fast in Europe. And Europe, and of course several Chinese manufacturers also now go for trucks. Just to give you an example, in Shenzhen, which is maybe nowadays the most innovative city in China, 12 million inhabitants, if I'm roughly right. By end of last year, they have finished the conversion of all their buses. They have 14,000 buses using for the public mass transport in the city, and by end of last year they have been all electric, all battery electric buses. So just to give you an example, European cities complain that they do not get offers for electric buses they want to buy. In one or maybe the most innovative city in China, they have already finished it. So that's really amazing. And now they do it for heavy duty trucks, so for collecting the waste or for construction machinery, they are now converted to all electric trucks. So that's really fast. And here this is an all electric plane, so that might be the most complicated piece to get it fixed there. But there is the target from Norway. Norway is also quite interesting because this is the country in the world with the highest share of electric vehicles per capita. So they're even more advanced than China. China has the largest number as a total, but they have 1.3 billion people, so that's not so easy to have it per capita. But in Norway they have it per capita. So in this year, the first half of this year, half of all sold cars had been electric cars. And this is the leading market in the world. And Norway has now the target, and this is very amazing because it's also the leading exporter in Europe of fossil oil and gas. But they have a very clever strategy, sell the fossil fuels to the junkies in the world, but don't use it at home. And that's really a clever strategy, because at home everything is based on renewable electricity. So the entire power sector is 100% renewable. The heating system, of course, there it can be really cold in the winter, is based on electricity, and now they fully electrify their transport sector. So that's really amazing. Maybe the leading country on a per capita basis in the world. And now they have the governmental target in the year 2040, all flights around Oslo, which is capital of Norway, 1.5 hours around, 500 kilometers distance, they should be all electric in 2040. So that's really amazing, but you find such startups. And the large airplane manufacturers like Boeing or Airbus, they currently start to invest in startups to be there. What does it mean for the energy demand if we would have such an energy transition also in the energy sector? And you can see it here. This orange means a direct electrification. This is mainly on the road. And then you see this green, this darker green, and this blue parts, and all in all is a huge electricity demand. So the total electricity demand by 2050 is comparable to the power sector, but this is not a transport sector. And there it starts by end of the next decade that we have more and more demand for liquid fuels, but based on electricity. So this is what I said in the beginning. Electricity plus water plus air, and then we can produce all fuels and chemicals. And this is needed here. And then you see some liquid natural gas, but based on electricity again, which may be needed for the marine industry or marine transportation. And then there is more hydrogen here, which may be used in shipping industry, maybe a bit on the road, but on the road is currently more clear it will be electricity and maybe a bit for aviation. So the point is, if this transition is done with these different fuels, and if we have a 100% renewable electricity system by the mid of the century, then the greenhouse gas emissions, which is here for the transport sector, it's in the same order as the power sector as of today, so roughly a quarter of all greenhouse gas emissions in the world. Then in 2050 we can be also at zero. However, and this is interesting or important for the next 10 to 15 years, in best cases we can get a stabilization, because it's so complicated to get this electrification started. It still takes some 10 years, let's say. And then we have a higher share of electricity in the power sector without greenhouse gas emissions, so without coal mainly. And then this overall greenhouse gas emissions can go down. Because the point is, if you have such a car and it's fully based on electricity, and all electricity comes from coal-fired power plants, then it does not make any difference whether it's fueled with petrol or with this electricity. The emissions are the same. So it only makes sense if it's green electricity. Okay, now let's come to the lithium resources. I think that should be most important part. Here you see a world map with the lithium resources in the world. And these very large spikes are where the lithium can be found. So there is some lithium in China, a little bit in North America, the rest is in Southern America, and this is Bolivia here. And this is the largest one of all. So this is an outstanding asset. However, there is not really nowadays a consensus on how much lithium is really available in the world. So there seems to be a factor of 3, 4 of difference around. So we have indicated, we did some research on that here in 3 or 4 different manufacturing potentials. So so this is a medium and high. This is very high and very low. Manufacturing potential. What you can see here is what have been historically produced. This is what is expected by financial analysts for the next few years. And based on this first data, such production profiles could be achieved. And this is for this century. So it's not anymore to 2050, but to the end of this century. And what is then important? What you can see, they're all in decline. So this is a very important message. We do not have enough lithium for all the batteries we might need in this century. So we did several scenarios, and whatever we did from now on in 50 years, 60 years, later 70 years, but 50, 60 typically, we had a strong final physical shortage of lithium. So the world would need more lithium to build all the batteries. This is, from a scientific point of view, not a huge disaster, because the point is one can in principle also build batteries based on aluminium, based on sodium, based on magnesium. However, what is working today is only lithium. So from that point of view, for now and maybe the next 10 to 20 years, there are only lithium batteries available. In the longer term, there might be more technical options. So there is currently research, even startups, but there is nothing close to be comparable to a lithium battery. And what is the consequences here? Here you see from these two maybe production profiles, this medium and high, how lithium would be available. And in a very ambitious energy transition scenario, this will be the demand. So the demand will be much higher than the production potential. The consequences, all producer countries in the world should be in a paradise situation. Because if the rest of the planet really needs and wants this resource, and only a few countries in the world have this resource for an acceptable cost level available, then these countries will have an excellent position. And this position will be for several decades. So in other words, this fortune should be used. So the manufacturing or production capacity of lithium should be, from my point of view, increased as soon as possible. But please be very careful that it's always under Bolivian control. Never sell the resources. Maybe the rights to extract it, and with a very high tax, and how this is typically done for such resources, but never sell the resources. It would be not clever from my point of view. So the resource is huge, and the value is huge. The global demand will be higher. So the advice would be, it could be for a fair industrial development, and that situation should be possible. It should have a very, very high opportunity for value chain integration. So from my point of view, it would be not clever to sell the lithium, it would be clever to sell the fully manufactured battery. Because if everyone on the planet wants to have the lithium, then the negotiation power here in Bolivia should be outstanding high to sell, sure, for some industrial consortia. The lithium is available, but we want to export the batteries, so please organize the rest as well. Very simple. And that generates cost, tax income, and steep increase in economic development, and finally strong economic growth. But I think that is mandatory. Do not start to export the lithium, at least not on a larger scale, but the products out of it. And of course, the resources itself should be never sold, from my point of view. This is a bit more technical. I want to go here a bit, because here you can see the industrial cost curve of lithium. And it's first the salt lakes in Chile, then the salt lake here in Bolivia, and then some other resources. And then from a specific point onwards, this is a cost diagram, what it would cost to extract it. So we know it's here a bit more complicated than in Chile, but not so much. So it can be extracted. However, then there's a kind of an unlimited resource available, but on a very high cost level. So that would be a kind of a bad luck if there would be a technological breakthrough here. So currently nothing indicates that. But the by far largest lithium resource in the world is in the ocean. So there is huge lithium resources in the oceans, but it's so diluted, so in a so tiny concentration, that it costs a lot of energy to extract it. And this energy which is needed to extract it, technically it's possible, that's not a technical issue, but it costs so much energy that it's so much more expensive to do it that no one is interested to do it. However, if there would be, due to whatever reason, a major breakthrough, then everyone in the world with access to coastline could produce lithium. But for the next decades, I would not assume it. And from the industrial cost curve, it's very clear here in the region is the least cost and the largest volume, so that should be a very prosperous future. And I don't want to go into detail from how the lithium is used. However, lithium will be maybe, let's say it will be very similar than silver in the past. So we know also very well from Bolivia that Silver had been extracted here, I don't know, for the last thousands of years, but most of the silver still exists in the world. So it had been maybe distributed around the planet, but it had been not wasted. It's still there. And the same will be with lithium. So this lithium metal will be converted to batteries. These batteries have a technical life in the end, 15, 20 years. And then these batteries will go to recycling. And in the recycling step, this lithium will be extracted again and used for the next batteries. Otherwise, this entire energy transition with batteries would not make any sense at all without this recycling step. But still, if this recycling is still done, there is still too less lithium in the world. But this will be also part of the game. But then, of course, more in the regions where most of those batteries are. So there's economic, powerful regions with high population density, China, Europe, North America, India. So there will be a lot of batteries in cars, stationary applications, and when they're at the end of the life, they will all go to recycling plants, and then lithium, but also other valuable elements will be extracted and then used again. But the point is, it will be never enough. Okay, and now at the end, I would like to show you a bit more what this power to X means, because that the lithium is a huge fortune for the country. I think this should be for most experts, as you are here in the room, already known. But this power to X, I'm for sure, is new. And power to X means the very least cost sites of electricity in the world have the best chances to attract the energy-intensive industry in the world. And by the way, it's not by accident that large aluminium plants are today located in Iceland and Norway. The reason why they are today on Iceland and Norway is there is very low-cost hydropower available. So due to that, they have huge ships transporting bauxite to Norway or to Iceland. There in the plants with very low-cost electricity, it's converted to aluminium, and this again is exported to the rest of the world. So we already see today how such a kind of global value chain works. And that will be in future for everything what is also based on this power to X. And here you see a kind of a diagram with chemicals and fuels. So it always starts with electricity, with electrolyzers, we get hydrogen. We need to get from somewhere the CO2. And the hydrogen and the CO2 together is this synthetic fuel, syngas, typically carbon monoxide and hydrogen. And with the syngas, then different chemicals and fuels can be produced. So the chemicals can be methanol or ammonia. What I mentioned before, ammonia is the starting point for fertilizers. With methanol, one can produce plastics, for example, or it can be also used as a fuel. So it can be used in a standard engine as a fuel. Methane can be produced, or so-called Fischer-Tropsch fuels, which is then diesel or gasoline or jet fuel, what we need for the airplanes. So, and that this is all needed very, very low-cost electricity. So that's the point, and I show you some examples, what we calculated in the past. So this is the value chain is power to gas. And then this gas, which is what we use today as a natural gas, so methane, and this is then converted to liquefied natural gas, and that can be traded globally. So it would the main flow would be we have renewable electricity. This is converted in electrolyzers to hydrogen. This hydrogen is converted in a step which is called methanation, with the so-called Sabatier process, invented again 100 years ago by a French chemist. And then this SNG can be liquefied. So as it's done since a few decades in several liquefaction terminals around the world. Started in Qatar, in the Gulf region, but nowadays done in all major regions in the world. And then with these LNG ships, it can be traded around the planet. And where it's imported, it can be regasified, and then it's again SNG. And as you can see here, the overall efficiency is around 57%. And this is a number we find in almost all of those conversion steps. It's between 50 to 60% efficiency from the starting electricity. But the point is, the lower cost the electricity is, the lower cost will be the final fuel by the final importer. So having the best site for solar in the world is of course an asset for such an industry. The same can be done with this power to liquid. So there again, it's now very similar. It starts with renewable electricity, with electrolyzer, then we get hydrogen. With the hydrogen, we get the syngas. There's some CO2 is needed, so CO2 comes from the atmosphere. Most of the energy which is needed for that is heat, but heat on only 100 degrees Celsius, but the heat is a waste heat from another process step, so if everything is integrated, the efficiency can be even increased. And then with this Fischer-Tropsch unit, which is again 100 years old, then one gets such a syncrude, and this can be then split into different fractions, and then we have jet fuel and diesel and naphtha, which is again another chemical which can be used for the chemical industry. And the overall efficiency, again, 50 to 60%, so 53 in that case. This is, you see, it's less complex. This is the Haber-Bosch process invented 100 years ago in Germany. It's power to ammonia in that design. So it starts again with renewable electricity, then electrolyzers with hydrogen, and then there is a so-called air separation unit, and the air separation unit extracts nitrogen from the atmosphere, and then the nitrogen from the atmosphere and the hydrogen is then converted into ammonia, and this ammonia can be used as a fuel, as a storage, or as a starting point for fertilizers. The efficiency here seems to be even more attractive, so that's even more than 60%. So that's highly attractive. And here you see we did a kind of a comparison of all what we have calculated there. So renewable electricity. So, and this, if it's calculated, so it's for a very cost-effective region in 2030. So we choose a region, I think it was in southern Algeria, in northern Africa, but here in the south of Bolivia, it would be the same or even better. So the renewable electricity generation cost is around 24 euros a megawatt hour here, but already for around 7,000 full-load hours. So that means for the best possible solar plants we know from Atacama Desert, they can run up to 3,000 full-load hours. So perfect sun and single axis tracking following the sun, then it can be on the very high level. And then further batteries are needed to bring it on a level which is close to the base load demand for the following synthesis steps. And then the storage may cost half of it. So maybe half is generation, 10, 12 euros a megawatt hour, and additional half for the batteries to get it close to base generation, because this is needed for these industrial processes. And this is the starting point. And then you see one can convert it to hydrogen, to liquefied hydrogen, to synthetic natural gas. It can be liquefied to liquefied natural gas. Then it can be traded around the planet, and you see even if there is 17,000 kilometers in between, that means one could start in Patagonia and ship it to Rotterdam in Europe. This is maybe 17,000 kilometers in between, and then it costs only slightly more. So this transport is not that relevant, so it can be globally traded, that's the point. And then it would be this SNG, so synthetic natural gas at destination. And we can have power to liquids, so this is the cost point here. We can have methanol cost point here, dimethyl ether, which is very similar, but we do not get soot in the burning process, so that's good for air pollution. And then ammonia here. And what you see here, this is the range of what the same chemicals cost based on fossil fuels. So it's very close to what the cost structure is with fossil fuels. So that means later than 2030, this would start to be beneficial. It would be economically very attractive if there would be a high CO2 price, because then this fossil fuel alternative would be higher in cost, or if we would get the cost of the electricity further down, or of such conversion units. So all in all, in the best sites in the world, this power to fuels and chemicals will start in the next decade, and it will have a major breakthrough. I think this is now more and more clear in the 2030s. So from now on in 15 to 20 years. And then this will be a huge industry all around the world, and the sites with the lowest cost electricity generation have the best chances. I will not go here in the details. There are many of those diagrams, and it may be all a bit confusing then in the end for you. But as you can see here, whenever it's in the red, then it's very attractive. And here you see southern Bolivia again, so Atacama Desert. And this is very competitive to all other regions in the world, but this is for 2030. The closer we are to 2050, the more competitive the region gets, because the more it benefits from the very low-cost solar and battery cost compared to other regions. In particular, good wind sites, as in Patagonia, then lose a kind of a competitive edge. I'm just looking what we should take best. This, for example, on these diagrams, maybe when you have then later on the presentation on your own, then you can better check in detail. The resolution of the beamer is a bit challenging here. But here you can see from 2030 to 2040 that more and more regions in the world switch to solar, because this dark brown red indicates how high is the share of solar from a hybrid PV, so solar wind plant, for these industrial processes. And you see here have been much more wind sites, and they're more and more captured by solar sites. Also in Southern or Latin America, you see there are more solar sites, and in 2050 this will be more intense. And the reason is that the cost from solar and batteries faster go down as from wind, and that makes it highly competitive. And here is a cost comparison from synthetic natural gas. This is liquefied natural gas, and these are synthetic liquid fuels, all for this cost point 2030, so when this revolution mainly will start. And again, when it's closer to red, then you see the least cost sites in the world. And for this synthetic natural gas, you also find here the region, but Patagonia is still the best in the world, and Horn of Africa is also quite attractive. When we come to LNG, it's Patagonia, and when we come to synthetic fuels, it's comparable. However, if you see, I've only shown here 2030, if you would see something comparable for 2040, then the solar regions in particular here would have a much higher relevant share. So the relative competitiveness gets stronger and stronger and stronger, the lower the cost of solar and batteries will be. This is then just for chemicals, so here is for methanol, this dimethyl ether, and for ammonia. And again, you can see that the region here is competitive also to others. However, at least in 2030, Patagonia is competitive. Here, this is South Morocco. Some parts of Sahara, Horn of Africa, Western Australia are really competitive. So now I'm very close to the end, and I just wanted to show you once how this CO2 direct air capture works. So this is from a startup in Zurich in Switzerland, but at least we have found 7 different companies doing that. There are 3 in North America, 1 in Canada, 2 in the US, and the other are all in Europe. And it works that low-cost electricity is needed, and then some of the electricity is converted in an efficient way to thermal energy, and then with thermal energy, so heat, it's around 100 degrees Celsius, and electricity, this is captured out from the atmosphere. And that will be very important for this power to fuels and chemicals processes. So also the cost will go down, so this is cost of capital. We did some estimates, so the chance is really good that the cost come down very fast, but of course different markets are needed, but seems to be available. So now let's summarize this with business opportunities, in particular here from the transport sector. So first of all, the electricity or direct electricity, this only works with lithium batteries today, and the best lithium resources are in Latin America. So this is a kind of economic development program the region should not withstand. And electricity indirect, here for liquefied fuels. It's mainly for marine and aviation. It's most competitive for the least cost of electricity sites in the world, which is Patagonia for wind and Atacama for solar, and these are the best sites in the world again. So the synthetic fuels can be globally traded as a commodity product, as today such products are traded. So diesel and petrol, or these products, are traded today also globally. So all forms of indirect electricity used in transport sector are hydrogen-based. So hence a global liquefied hydrogen trade would enable Latin America to establish a huge global export business. So I think that's the main message here. And that's all. So the key takeaways I already had in the very beginning. I let them here, but of course I don't want to forget to thank my team, because this very high international team really allows us to do this research on a global, local scale. And from Latin America, there is Javier here. He is from Mexico. And you cannot see here, but there is Larissa from Sao Paulo. So at least 2 from the region are also in my team. And then many thanks, and I will be very happy to get questions from you.
Fuerte aplauso, por favor.